we are done with stochastic models where we have done three things on last class. One is autoregressive model AR as we call it, and moving average model MA as we call it. And then we combine autoregressive and moving average model together and we say ARIMA. ARIMA stands for autoregressive integrated moving average model. ARIMA model. ARIMA. ARIMA. ARIMA model. So we have done it. Today we will talk about stationarity and non-stationarity of time series data. So without wasting time, let me share a PPT to first go through the ideas and basic concepts. And then when the basic concepts are understood, we will move to an Excel sheet. I'll take an example and show how to test for stationarity. And if it is non-stationary, how do I treat the time series data to get the stationarity? So let me share a PPT first. Yeah, so I have shared stationary and non-stationary models in the PPT. You can see. So first of all, what is stationary model in a time series forecasting? What is stationary model? So in the time series data modeling, stationarity refers to a property of time series data where its statistical characteristics. What are the statistical characteristics? As a mean, variance and autocorrelation structure remain constant over time. So this is very, very important definition of stationarity from the exam point of view. You have to remember what is stationarity for time series data, where the mean variance and the autocorrelation structure remain constant. So what is autocorrelation structure? We will see that later on. And so structure remains more or less constant over time, then this is known as stationary model. So what is the condition? Once again, the mean, the variance and the autocorrelation, all three remains constant over time. So these are conditions of time series data to remain stationary. So if it is not constant over time, if mean value changes like moving average and the moving variance changes, then autocorrelation factors SEF1, SEF2. Last class we have shown you SEF1, SEF2, SEF3, etc. Autocorrelation factors changes over time and does not remain more or less constant. Then we say those time series data can be called as non-stationary data. So stationary, non-stationary. Stationary data where moving averages, moving variances and autocorrelation SEF1, SEF2, SEF3 values, if more or less constant, then we say it is a stationary data. Otherwise, we say it's a non-stationary data. Then why stationarity matters? Why is it important for us to understand whether the time series data is stationary or a non-station or is it non-stationary? So most forecasting models like ARIMA, we have learned about ARIMA as a forecasting model, assume that underlying data is stationary. It is easier to model and predict. So stationary models are easier to model and easier to forecast or predict future outcomes. So stationarity is a requirement of fundamental predictive analytics on a time series data. And the relationship observed in the past are more likely to persist into the future. If it is stationary, then the relationship observed in the past are more likely to persist in the future. What does it mean? That means the past trend will continue. So we can forecast with greater confidence on the forecast. So this is why stationarity matters. So if the data is non-stationary, we decompose and then we make it stationary and then forecast. So that is the purpose of ARIMA. Now there are two types of stationarity we see. One is strict stationarity. The entire time series data distribution of the series does not change over time at all, strictly stationary. And there is something called weak stationarity or a covariance type of stationarity. Only the first two moments, mean and variance, are constant, and the covariance between values depends only on the lag between them, not on the time itself. So covariance between auto regression Autoregressive terms, say autoregression 1 or autoregression 2, the covariance terms does not remain constant. Correlation remains constant, but the covariance or the correlation covariance, whatever, SEF1, SEF2, they do not remain constant. This is called weak stationarity. So what is strict stationarity? I repeat, mean moving average, variance moving variance, and autocorrelation SEF1, SEF2. That means the autocovariance also. They remain constant. All three of them remain constant. Now, if all three of them remain constant, that type of stationarity is known as strict stationarity. But what is weak stationarity? When the mean moving averages remain constant, more or less. Variance, moving variance remain constant, more or less. And so these two, moving average and moving variance, they remain more or less constant. But the moving covariance or moving autocorrelations, they are not constant. SEF1, SEF2, they are not constant. So that you need to understand. So that is called weak stationarity. Now stationary models are those designed to work with stationary data. Common examples is AR. I will solve AR model once again. MA, moving average model, will solve moving average model once again. And ARMA or ARIMA model combine both AR and MA components. Auto regression integrated with moving average models. So these are common moving stationary models. So if the data is non-stationary, we convert them to a stationary data, and then we assign ARIMA or AR or MA models. These are common stationary models. And the original time series is non-stationary, that shows trend and seasonality both. It can often be transformed into stationary data using techniques such as differencing, log transformations, or detrending or deseasonalizing. So I repeat, if the data is stationary, very good. We can directly apply AR model or MA model or ARIMA model, AR, MA or integrated AR and MA, that is ARIMA. If the given time series data is non-stationary, then what do I do? Which shows trend and seasonality both. Then we have to use some technique to convert the given non-stationary data into stationary data. What are those techniques? What are those common techniques to convert stationary time series data? Sorry, to convert non-stationary time series data into a stationary time series data? Differencing is one such techniques, log transformation, second such techniques, or detrending or deseasonalizing such data. Once the stationarity is achieved by either differencing or log transformation or deseasonalization, then we can apply model like AR, MA or ARIMA if differencing is involved. Then can be applied for effective forecasting. So non-stationary model, first you check whether it's stationary or non-stationary. If it is non-stationary, very good. Then you apply AR, MA or ARIMA. If it is non-stationary, then you convert them to a stationary and then apply AR, MA or ARIMA. This is the structure. So I summarize once again. Given time series data, first check whether the data is stationary or non-stationary. If it is stationary, fantastic. Just directly apply AR, MA or ARIMA for forecasting purpose. If it is non-stationary, then first convert them into a stationary data by using differencing technique or log transformation technique or detrending or deseasonalizing technique. Once it is transformed into a stationary data, then again safely you can apply AR, MA or ARIMA kind of stationary model. So ultimately we will come back to AR, MA or ARIMA. AR is autoregressive model, MA is moving average model for forecasting, and ARIMA is autoregressive integrated with moving average model, called ARIMA in short. So this is the common approach on any time series data. Now to how to achieve stationarity, let's go deeper into it. So there are three key techniques to transform non-stationary time series data into stationary data. An essential step before we applying models like ARIMA or AR or MA. First is differentiating. What is differentiating? Removes trend, sometimes seasonality, by transforming the series into changes rather than absolute values. So any time series data, rather than absolute value of the given time series data, we find the change or the difference between today's value and yesterday's value. This year's value minus previous year's value. So current value minus previous value. So that's called first order differencing. Differencing series is yt minus 1. What does it mean? Current value minus previous value. This is called first order differencing. What is second order differencing? Is differencing of the differencing. Again the first order series if needed. If needed. So this is yt double dashed is yt dash minus yt minus 1 dash, that is first differentiated value is subtracted from the second differentiated value. So this is called second order differentiation. So generally we have to stick to first order and second order. Very rarely we go to third order differentiation. So if you have trend and seasonality both, then we may have to go to second order differentiating. And when to use? So use first order differencing to remove the linear trend. And if you have linear trend along with seasonality, use seasonal differencing yt minus s, where is the seasonal period, to remove seasonal patterns. So sometimes if you have seasonal pattern like 4 quarters, quarterly seasonal, then we subtract yt minus 4. T minus 4 is a similar quarter last year. So we subtract yt minus 4 to remove the seasonal trend as well. So sometimes we do yt minus 1, the first order, and for the seasonal trend we do sth order. S is the seasonal periodicity. Suppose 4, so yt minus 4. So that's what we call it fourth order differencing to remove quarterly seasonal data. Fourth order differencing where s equal to 4. So this is the first method called differencing. Second method is called log transformation. It stabilizes the variance across time. Non-stationarity series often show increasing or decreasing variability. The variance or standard deviation, it changes. Logs can compress large values and stretch small ones, and that's why it stabilizes the variance. If the variability is very high among the given data over time, then generally we use log transformation to compress the large value and stretch the small values. So apply the natural logarithm or log base 10 to each value. So generally we apply natural logarithm, not the natural, not the e based logarithm, not the exponential e based logarithm. Apply the natural logarithm, e based or log based. So you can do yt dash is log of yt or ln of yt. Either natural log, that is to the base e, or log to the base 10. Both are applicable, whichever is comfortable. But generally as a practice we take natural log. When to use log transformation? When variance increases with the level of the series, common in financial or economic data, we use log transformation. And can be combined with differencing if both trend and variance need to be addressed. So we can do differencing and then we can apply log. We can do that. If we see there is a trend and seasonality present as well as variance changes over time, and both of them are visible, both of them are occurring in the time series data, then we can apply differencing, say first order differencing, and on top of that we can apply the log transformation. So was a common example of log transformation. Suppose the sales data grows exponentially, 100, 150, 220, 330, very high values of yt. This is y1, y2, y3, y4 is a given time series data. We can take log, that is base 10 of this 100, 150, 220, 330. So we can take this is 4.65, 5.4. This is the L. This is not log. This is ln. My mistake. Sorry. This is e base. E to the power 4.6 is 100. So we can take log transformation. Next is detrending. What does it do to the given time series data? It removes the underlying trend, linear or non-linear, from the series to isolate the stationary component. So we need to isolate the stationary component. So first we fit a trend line, that beta 0 plus beta 1 t plus et. Then subtract the fitted trend from the original series. that is called residual, is called detrended series. This is known as residual. So we calculate residuals, that is the given time series data yt minus the trend line value, that is beta 0 plus beta 1t. So this we subtract and we get the detrended series, the residual epsilon t, that is residual, that we can find out using this residual technique. Alternatively, use time series decomposition, STL decomposition, to extract and remove trend. That is also we can do to remove the trend, the stationary part of the data. So when to use? When a series shows a smooth deterministic trend, a very nice linear trend or a non-linear trend is visible on a data, then you can apply the residual technique to make it stationary. So these are three common techniques to achieve stationarity. One is differencing, second one is log transformation, third one is detrending. So I will summarize how to choose the right technique to achieve stationarity. If the problem is only trend is visible, we do a first order differencing or detrending. So either number 1 or number 3, both are possible. If variance is instable, variance instability, variance is unstable and is increasing, we can do a log transformation. We see trend plus variance both changing over time, then we do log plus differencing. And if only the seasonality, we do seasonal differencing or decomposition. Seasonal differencing is yt minus s, where s is the periodicity of seasonality. So this is a key to remember, that how do I apply the method for stationarity and choosing the right technique. And how do I identify stationary or non-stationary data? This is very important. How do I know the data is stationary or non-stationary? So identifying whether data is stationary is a crucial step in any forecasting process. We can identify whether a time series data is stationary or non-stationary using three ways. Either you can do a visual check, or a statistical summary, or a formal statistical test. So first is the visual inspection. We plot the time series data and look for signs of non-stationarity. Trend, upward or downward slope over time. This is a sign of non-stationarity. Seasonality, regular patterns repeating over fixed intervals, a sign of non-stationarity. Changing variance, increasing or decreasing spread over time. This is a sign of non-stationarity. Mean and variance look constant over time. Likely the data is stationary. So tip, use moving averages and rolling standard deviations if they are constant. So moving averages and moving standard rolling variance and rolling standard deviations to see if they are constant. If they are more or less constant, then we say visually we can see that statistically also summarize possible. So next is statistical summary. Divide the series into two or more segments, first half, second half, and compare mean and variance across segments. If there is a significant shift, the series is non-stationary. So we can make up into two segments or three segments or four segments and check the average and variance of those four segments. And if they are significantly different, then we say data is non-stationary. Or you can simply see the moving average is constant or moving average is as a trend, or moving rolling standard deviation is constant, rolling standard deviation has a trend. That also another way of statistical summary. And there are formal statistical tests which we are not touching or not discussing. There are two types of tests called augmented Dickey-Fuller test, we known as ADF test. So ADF test assumes as a null hypothesis the series is non-stationary, and if the p-value is less than 0.05, it is stationary. This is called ADF, augmented Dickey-Fuller test. So we are not touching it. And there is another test called KPSS test, called Kwiatkowski, Phillips, Schmid and Shin test. KPSS test assumes just the opposite. The null hypothesis is the given time series data is stationary, and we check for KPSS test. If the p-value is 0.05, we reject H naught, the series is non-stationary. So use both ADF and KPSS for cross validation. they test opposite hypothesis basically. One is augmented Dickey Fuller test, which is the most common test used for stationarity check, and little uncommon is KPSS test, which is Kyout, Oski, Phillips, Schmid, and Shin test. So this is about how to identify stationarity and non-stationarity. So I'll start from here. I'll take our data and first identify stationarity or non-stationarity. If they are non-stationary, then we will convert them into stationarity. Either we will using differencing, log transformation. We will use log plus differencing plus log plus differencing, and also we'll show a seasonal differencing or decomposition. And also we'll see a detrending using the residual technique. A detrending using a residual technique. And we can also do a time series decomposition technique. So let us revise all three. We'll take our data. We'll first check whether the data is stationary or not. And if it is non-stationary, we will convert them to stationary. And then you can apply ARIMA, AR and MA. So this is what is today's lecture all about. So now I will unshare the PPT and open a fresh Excel sheet to check some data, and then we'll see how it checks. So now I will share a blank Excel sheet. I hope you can see the blank Excel sheet. So suppose I have yearly data, sales data. Sorry, I have monthly sales data. So suppose we have 24 months of data, Jan, Feb, March, etc. Yeah, so 24 months of data. So we can have a serial number also here, just for my reference. And let us assume some sales data. Sales revenue in rupees 1000. So this is for a particular product in rupees 1000. So let us take some data, creating some random data. So suppose a given data. So first I check for stationarity. So what I'm learning now, we are checking for non-stationarity for a given time series data. So ready everyone, we are checking for non-stationarity for a given time series data. Great. So if you remember the PPT slide, we check for non-stationarity in different ways. First is visual inspection. So first thing is we'll plot a scatter plot. We insert a scatter plot. So this is the sales revenue. There is no value below 150. So I make the minimum value 150 to exaggerate and highlight the fluctuation. So this is the sales revenue. I do not see any upward or downward trend visually, but I see some random fluctuations, maybe a seasonality. So visually, I do not see any trend or any seasonal pattern. So neither we see any trend nor we see any seasonal pattern that it is revolving every 4 months or something. We do not see much of trend visually. So visual inspection is done. Now we will see moving averages. Suppose we have a 4 months moving average, or maybe a 3 months moving average, or I can do a 6 months moving average. We can break down the data into 4 parts. So first is breaking down data into 4 parts. Four parts, 24 months of data. So 4 parts will be 6 months, 6 months, 6 months, 6 months. So the mean variance. So I'm calculating mean and variance for the first part. This is the first part, and then we can done. So we have done 4 parts. So breaking down into 4 parts and checking the mean value more or less same, or variance more or less same. So this is the mean of, that is the average of first 6 values till June, and variance var dot s, I'm taking a sample variance of till June. So this is the variance, and we can calculate the standard deviation. We can calculate the standard deviation also. STDV dot S of the first 6 months. 24. So now we can drag 177, 173, 172, and now look at the variance. Right. So now we see, let us plot this. Let us plot this mean values. Oh no. So let us plot this. This is a merged cell, so it's not taking the chart. So we have broken down this entire 24 months data into 4 parts and then taken the mean value. So visually we can see 174, 177, 173, 172, not much of difference. So let me copy these values. And let me have this first part of the data, second part of the data, third part of the data. So mean is 174. This is 177. This is 173, and this is. So we can now plot these mean values. So we can see the mean values more or less, it gone up and gone down. So I'm not sure is it stationary enough or not, because mean value is slightly changing. So this is the mean value. Now the variance value, let me see the variance value. 581, 104, 249, and 284. So variance value really changed, I believe. Gone down and slightly gone up. So variance values also changed. Now the standard deviation will follow exactly same as variance because it's the square root of variance. 24 and then 10 and then 15 and then 16. So the standard deviation also changes. So these are the so this is a technique where I have broken down the given time series data into 4 parts and checked for whether mean variance and standard deviation is changing over time. We can also do a moving average and rolling standard deviation. So we can do a 4-period SMA. You know how to calculate SMA. And see, and also we can do a 4-period rolling standard deviation. We can do a 4-period rolling standard deviation. I've just removed the graph slightly. I'll share this Excel sheet with you. You can see these plotted graphs on the right side. I've not deleted them. I just set them aside. And we have this. Now I'll do a 4-period SMA and plot it to see. So 4-period SMA, I'll just plot it here. Average of first 4 values, and then we roll it down till here, I believe. Yeah, no, one more row. Yeah, this is the last legitimate value of SMA. So these are my SMA values. I ignore the error because Excel is thinking I've made an error. And similarly, we can have stdev.s, the rolling standard deviation, stdev.s of the first 4 values. That is 25.4647, and we can drag. Like this is the last legitimate value. So now I'll plot the 4-period SMA graph and see whether there is a moving average is more or less constant or not. No, moving average itself is fluctuating, so the average is not constant. So from all indication, we see the data is non-stationary, and this is non-stationary data. So average changing, moving average changing, 4 parts average. I have done 4 parts average, which is 174, 177, 173, and 172. These 4-part average values changing, even moving averages, 4-period moving average value also changing. So this is 4-period moving average SMA, and then I will plot the 4-period rolling standard deviation. We'll plot it. This is 4-period rolling standard deviations. Standard deviations came down and then again gone up. So all the visual inspections and the rolling averages, moving averages, rolling standard deviations, these 2 techniques are applied, and from both these techniques we see data is non-stationary, not because of the trend. I do not see any upward or downward trend. I'll go back to the original graph. I don't see any upward or downward trend. We can see only a sidewise trend, which is almost constant. But the trend may be absent, but the mean and variance over time is changing. So I repeat. So how do I determine stationarity? So first definition of stationarity. So mean and variance should not change, and autocorrelation structure, that also should not change. That's the stationarity. So now I'll check for autocorrelation factors. So visual inspection done, moving average and rolling standard deviation done, and breaking down the data into 4 parts and checking for the values of mean, variance and standard deviation, that also done. So mean, variance, standard deviation, these are changing. These are changing. Now we can also check for autocorrelation factors whether they are changing or not. Now I'll do for the autocorrelation factors. What I'll do, I'll copy this data below to get the autocorrelation factors. So now checking for autocorrelation factors. ACF. So first is we can look at lagged series 1, lagged series 1, and we can calculate lagged series 2. I just show autocorrelation factor. Lag series 2, we can calculate lag series 3, lag series 4, lag series 5. Let's create 5 autocorrelation factors and see whether they are changing. So lag series 1 is, this is the next value. So we drag. This is lag series 1. Lag series 2 is, this is the March value. Sorry, this is the March value. And we drag. Last two values will be blank, obviously. And lag series 3, this is the April value. And lag series 4 is, this is the May value. And lag series 5, this is the June value. Now we can drag. Now obviously last values will be 0 and this will be 0, this so blank. So we have created 5 lag series 1, lag series 2, lag series 3, lag series 4 and lag series 5. Now we can calculate autocorrelation factors SCF1, SCF2, SCF3. SEF, and we have lagged series. So lag series number. So 5 lag series, we calculate autocorrelation factors, SEF1, SEF2, SEF3. So core L of the original time series data, I just skip the December part because we need the equal length of data. So lag series 1 has 23 values and original time series data has 24 values. So I have taken 23 values, comma, lag series 1. So this is minus 35%. SEF1 is minus 35%. Now SEF2 core L of original time series data, I skip 2 values. I'll take 22 values because lag series 2 has 22 values, comma, 22 values. So this is minus 15%. So SEF values are changing. And then lag series 3, I take the original time series data and take 21 values, 3 values I omit, and comma, sorry. We have core L. I highlight the original given time series data and remove 3 values. I have taken 21 values, comma, lag series 3. So this is 6.4. Now these autocorrelation factors are drastically changing, minus 35, minus 15, plus 6.4%. Now the fourth lag series, I use core L of the given time series data. I'll skip 4 values, I'll take 20 values, comma, and the fourth lag series values. So this is minus 9.3. Again, autocorrelation factors are fluctuating. And the fifth lag series, core L, there are autocorrelations. I skip 5 values, we take only 19 values, comma, and lag series 5, 83%. Now, ignore error. If I plot you see the SEF factors, how widely they are varying. You can see SEF factors. I plotted the SEF factors, autocorrelation factors. So this autocorrelation factor again telling us this data is non-stationary. So I repeat, we are checking for stationarity of data, non-stationarity of given time series data. First approach, I have broken down this data into 4 parts and checked for how mean, variance and standard deviation changes, and we have seen them in the blue colored graph. I color coded the graph so that there is no confusion. In the blue colored graphs, we have seen the mean, variance, standard deviation fluctuated considerably to indicate this is a non-stationary data. Then you have taken 4-period SMA and 4-period rolling standard deviation and plotted it to show that 4-period SMA and 4-period rolling standard deviation both have changed substantially, showing that mean and variance must be changing over time. Mean and variance must be changing over time. But we don't see any trend. So trend is not there, but mean and variance changing over time. There's a lot of fluctuations. Also, we have done an autocorrelation factor called covariance check. Autocorrelation factor for lag series 1, lag series 2, lag series 3, lag series 4, lag series 5. So 5 SEFs have done. SEF I, I stands for 1, 2, 3, 4, 5. So we have SEF1, SEF within bracket 2, SEF within bracket 3, SEF within bracket 4, SEF within bracket 5. We have plotted SEFs. SEF stands for autocorrelation factors. Autocorrelation factors, that is the full form of SEF. And we have done an SEF also considerably changing. So covariance also considerably changing. We can also find auto covariance. Autocorrelation is similar to auto covariance. We can calculate auto covariance also, which is similar to correlation, because correlation is covariance divided by the product of standard deviations. So it is equivalent to calculate auto correlation to auto covariance, or we can also calculate auto covariance factors. Instead of corel, we can use covar.s. We can use covar.s. So if you remember, we say stationarity is achieved when mean variance over time does not change, and covariance or correlation also does not change over time. So we have strong stationarity here because mean and variance also changing over time, and autocorrelation also changing over time. So we have strong stationarity or strict stationarity. What is weak stationarity? Or sorry, strict non-stationarity. And what is weak stationarity? When mean and variance changes, but mean and variance does not change, but covariance changes over time, we say weak stationarity. So this is a very strong case of non-stationarity, neither mean and variance remaining constant nor the autocorrelation remaining constant. So these are the strong case of non-stationarity. So, and we can also perform something called ADF test, that augmented Dickey-Fuller test. Now we'll perform augmented Dickey-Fuller test. So let me check how augmented Dickey-Fuller test can be performed. So we first find the differencing series, and then we find the lagged series, and we run the regression. So I copy the given time series data. I ignore the month, I just take 1 to 24 as a serial number, and I copy it here for the ADF test, augmented Dickey-Fuller test. So what we can do, I just save this file, because if it goes away, it will be a major problem. So we have the serial number, month number 1 to 24, and the sales revenue for a particular product in rupees 1000. And now I will first calculate the differencing series. So we say the differencing 1 series. So differencing 1 series. Now how to calculate differencing 1 series? This is 151 minus 193. And we drag. And last value we delete. So this is the differencing 1. What is differencing 1? Second value minus previous value. This is third value minus second value. This is fourth value minus third value. This is fifth value minus fourth value, and so on. This is called differencing 1 series. Differencing two series will be third value minus first value, fourth value minus second value, etc. I'm not using differencing two series, I'm using differencing one series. So this is done. Differencing one series is done. After differencing one series is done, then we can do a lagged series. Lagged series 1. We can do a lagged series 1. Lagged series 1 already created here. I just copy and so this is a lagged series 1. So what is lagged series 1? This value is nothing but serial number 2. This value is nothing but serial number 3. It's called lagged series 1. So we have done differentiating series 1 and lagged series 1. So these are two things I need to perform an augmented Dickey-Fuller test, ADF test. Differencing series 1 and lagged series 1. Fine. Great. Very good. Now very simple. Now we have to perform a regression and we see the dependent variable will be the differencing series and independent variable will be the lagged series. So what I'll do a simple swap here so that I'll take this in the x-axis and that in the y-axis. So this I'll take at the x-axis. So lagged series will be taken as x-axis x and differencing series is taken as y. So taking lag series as x axis and differencing series as y axis, we are performing a regression. So you can performing a regression. I am doing it. First, I can visualize that scatter plot. You can visualize a scatter plot here for ADF test. There is no value less than 120. So this axis I can make minimum 120. Yeah, there's no value in fact less than 140. I can make it 140. So this is the differencing series and we can see the regression line here. We can plot a trend line, linear with 67% R square, not bad. So now we have to perform the coefficient of yt minus 1 for 5% is minus 2.9 basically. So let me check. I will perform. I'll go to data analysis, regression, and y range is the differencing series and the x range is, and we get the output suppose here. Yeah, we get the output. So this is minus 237 intercept, x value is 1.37. P value is substantially small. This is also substantially small. So both p values are very, very small. So in ADF test, we take the null hypothesis H0 as series is non-stationary. There is a null hypothesis. And how do I know it is the final value? Which one shall I check? We check the coefficient of the uh, independent variable, coefficient of independent variable, that is 1.35. It's very, very important value. Coefficient of is 1.35, and we check T stat for it is 6.58. So this is a very, very important for me. 6.58. Let me color it in a slightly different way. 6.58. So if this is more negative, even lower than minus 2.9, then the series is stationary. If if this is more than the critical value, that is roughly around minus 2.9, more positive, then series is non-stationary. So I say the T stat value corresponding to the coefficient of lagged series, that is x, is 6.58. Am I right? T stat is 6.58, which is more than minus 2.9, indicating that we accept the null hypothesis. So here p value is less than 5%. So we accept the null hypothesis that the series is non-stationary. So we performed an ADF test, which is augmented Dickey-Fuller test, by just lag series 1 and differencing series 1, differencing one series as x-axis and y-axis. We got the scatter plot and the regression equation and R square. We also got the T stat corresponding to the x variable coefficient. The p value is of course less than 5%. So we accept the null hypothesis. And we say the series is non-stationary. So we have done first part of our uh, topic today. We have taken time series data and we have done the check for non-stationarity. How do I check for non-stationarity? First, we have taken a visual check. There is no trend, but it's fluctuated heavily. Then we broken down the data into 4 parts and checked how mean, variance, and standard deviation changed over time. It has got a substantial fluctuation. Then to confirm that, we taken a 4-period SMA and a 4-period rolling standard deviation and plotted them here. 4-period SMA and 4-period rolling. It also substantially changed. Now, by now we are sure that the series is non-stationary. We have gone ahead and checked for autocorrelation factors, ACF. I have checked with 5 lag series 1, 2, 3, 4, 5, and gone for 5 different autocorrelation factors, SEF1, SEF2, SEF3, SEF4, SEF5. And then we have plotted the SEFs here. SEF value substantially changed from minus 35% to plus 23%, showing non-stationarity. And then finally, we have performed an augmented Dickey Fuller test by taking lag series 1 and differencing series Y1 and perform a regression analysis and checked for the coefficient of the lag series. T stat is 6.58, p value is less than 5%. So we accept the null hypothesis, which was series is non-stationary. So no, augmented Dickey Fuller test again shows us the series is non-stationary. So now we will go to the second part of our today's class, that if the series is non-stationary, how to convert them into stationary. So that I will copy this time series data and paste it here. Yeah, now you are ready. The second part of today's topic, that how to convert a stationary data into a non-stationary data. How to achieve stationarity. From a given non-stationary time series data. Right? So here autocorrelation factor changed, mean variance changed, but we don't see any trend. We didn't see much trend on the visual inspection. That we need to realize. So if you remember, we have already learned that if there's only a trend, then we can do a differencing or detrending. If there's a variance instability, we can achieve log transformation. If the trend and variance both changes, we can see, then we see the log plus differencing and the seasonality, seasonal differencing or decomposition. So first I will do first order and second order differencing, and we achieve the stationarity of the differencing data. There is no seasonality involved, so we do first order differencing and second order differencing. So I'm doing differencing now. I'll do differencing 1 and differencing 2. So differencing 1 is 151, the February month data minus 193. So minus 42.8. So this is my differencing 1 series. I remove the last data. So this is a differencing 1 series. So I plot the differencing 1 series and see how differencing series fluctuates. So differencing 1 series substantially fluctuate, and it's not came down to standard. So they have a good amount of variations in differencing 1 series. Now there is something called differencing 2 series. second order differentiating. So they take the differencing series and then they do it. So differencing series will be 47.5 minus 42.8. So now I can plot the differencing 2 series. That also fluctuating substantially. But you see the fluctuations died down a little bit. Now we can also do a differencing 3 series. Which I can do this minus this. Let me see whether the differencing 3 series gives me better input. Yeah. Again, this is fluctuating. So after doing differencing 1 series, differencing 2 series and differencing 3 series, the stationarity is not achieved. That means differencing is not an appropriate technique to achieve stationarity for this given time series data. So I repeat, differencing can be used only when you have a trend. First order differencing can be used to achieve stationarity of a data when there is a trend. The original data was not having any trend. His mean variance was changing, autocorrelation was changing, but trend was not visible. So differencing is not an appropriate technique to achieve stationarity. So we have tried differencing 1, differencing 2, differencing 3, yet the fluctuations are still very prominent and stationarity is not achieved much. So we can say that trend was not a problem in the time series data. So trend was not there. So we are using a wrong technique to remove non-stationarity. So differencing is not an appropriate technique. Next, I can do a log transformation. So this is using differencing. So I can use A using differencing technique. So I'm using differencing technique. We could not achieve the stationarity. I just conclude here. Using differencing technique, we could not achieve stationarity because differencing technique is used to convert into stationary data if the original time series data shows a distinct trend. So this technique is not useful. Why not? Because original time series data was not showing any trend. So using differencing technique, we could not achieve stationarity. Now let me see a log transformation. So what I'll do, I will copy this data and now we'll use the second technique using log transformation. Logarithmic transformation. Although any one is good enough, but I will show 2 logarithmic transformation. ln natural log ln series and log, both I will show. Ln is to the base e and log is to the base 10. So I am just getting the log of these values and see how these values behave. So ln of this data and log of this data base 10. Now we can drag. So let's see a log series if I plot. This is a log series. The fluctuations are narrowed down to a very small level between 5 to 5.3. This now become very stationary between 5 to 5.3, and similarly you can see these are between 5 to 5.3, narrowed down the fluctuations. And if I see log series, this will be between 2.18 to 2.3, further narrowed down between 2.18 to 2.3, very narrowed down. So log is an effective way to narrow down the fluctuations to only between 2.18 to 2.3, and natural log we have taken, this is between 5.02 to 5.3, within that. So log successfully transformed the given time series data into stationary data. Now we can apply AR, MA and ARIMA, whatever model we have. We'll revise AR, MA and ARIMA model once again in the next class before we close the discussion. Next class we'll do GARCH model and an ARIMA model. But using logarithmic transformation, we can make this kind of series where the trend is not visible, but mean and variance changes substantially. This is a very effective method. So I'm putting a conclusion here. Using logarithmic transformation is an effective technique in this case. Why do I say so? Because the trend was not prominent, but mean and variance was changing substantially over time in the given time series data. So I made a very vital conclusion. Using logarithmic transformation is a very effective technique in this case to achieve stationarity. Effective technique because the trend was not prominent in this case, but mean and variance changed substantially. So now I will show one more technique, that is detrending. Detrending using residuals. The third technique I'll show, detrending using residuals. But that is used when seasonal, when trend is there. So here trend was not there. Still I'll show detrending. The third method, I'll copy the given data. using detrending the series. Detrending technique using residuals. So how do I create a detrending technique? First, we will fit a trend line. First, we'll fit a trend line. What I'll do, I'll ignore the month and just delete the month, and we put this as the serial number as x-axis and the given sales revenue as in y-axis. Suppose we now we put a scatter plot. This is a scatter plot. This is a scatter plot. Now we can calculate the residuals. There is no data below 150. So what I'll do, I will vertical axis will format to 150. So too much of scatter. So yet we'll try to fit a trend line. There is no trend here, so detrending is not an applicable method. I'll comment about it later. I just show you the technique. So we have a trend line with only 0.8% R square, not even 1%. 0.8% R square value. You can see that. The 0.8% R square value. Too much of scatter. Too much of scatter. So I'll calculate. So you know the slope and intercept. I'll just compute it once again and then do a trend line data and the residuals. So do a trend line data. Trend line data is beta 0 plus beta 1 t, that is slope and intercept. So beta 0, beta 1 values, I will just put it here. Beta 0 is the intercept. And slope is beta 1. So intercept is intercept. Y values are here, comma, x values are here. So intercept is 177.1, as we already know that from the scatter plot, 177.11, correct. And slope is minus 0.213 equal to SLOPE. I'm just verifying minus 0.213. First the y values, comma, then the x values. So yeah, minus 0.213. So these are my trend line data. And then the residual. So residual is YT minus Y. This is YT dashed. And this is residual is YT minus this. Yep. So trend line data is x equal to 1. So beta 0, 177.11, dollar, dollar. plus beta 1 into t. So minus 213 dollar into 1. So first value is 176.89 and residual is 193.9 minus 176.9. So 17 is the first residual. And then we have all the residual values and all the trend line values. And now we see the stationary component, which is the stationary component we subtract. And if we have a trend, now you see the residuals, are they stationary? The residuals, is the residuals fluctuating or not? So look at residuals highly fluctuating. So these are the residuals. You can see the residuals highly fluctuating. So these are the residuals. So residuals are not stationary. That means we could not achieve stationarity using the detrending technique, the residual technique. We could not achieve stationarity. Why? Because original given time series data was not having any trend. So trend removal was not our primary objective or primary purpose. The non-stationarity was not due to trend. Non-stationarity was due to change in mean and change in variance values. So that you need to identify why the data becoming non-stationary. Is it because there is a trend, either general trend or a seasonal trend? Or is it because the trend is not there but mean and variance changing over time? Or is it because of both? The trend is also visible and mean and variance changing over time. Depending on these factors, we employ a method of creating stationary data out of a non-stationary data. So this is not an applicable method. So I put a comment. In this case, detrending was not an appropriate method to achieve stationarity from the given non-stationary data. Because why do I say that? Because the original given time series data did not show any trend. So trend was not there, so detrending was not an appropriate method. So log, till now you see logarithmic transformation was an appropriate method to achieve stationarity. That I have already commented here. To achieve stationarity, using logarithmic transformation is an effective technique in this case because the trend was not prominent. The mean and variance was changing substantially over time in the given time series data. So that is the comment that we have made earlier. So this is the detrending technique. And now we'll see how we STL decomposition. So now I'll do a time series decomposition. STL decomposition is known as seasonal trend decomposition using LOESS. So on the same data, I'm performing a time series decomposition. Is another way other than detrending that we can separate out the stationarity, the stationary component. This is the last method for the day. So what we are doing now is a time series decomposition for trend, seasonal and remainder component. So I'm just putting a comment here. The seasonal trend decomposition is a powerful technique for breaking a time series into trend, seasonal and remainder or residual components. So what I'll do, I will first copy the data. This is a 24 months data. So what I'll do, I'll 12-month SMA. So this is the trend component. This is called a trend component. Trend component using a 12-month SMA. So I'm using a 12-month SMA. I am writing it here. So average of first 12 values, and then we drag. We'll drag further. No, the last value is wrong. So 172.95 is the last legitimate 12 period SMA value. 172.95 is the last legitimate 12 period SMA value. So 12 period SMA, I have taken the average of first 12 values. Then I dragged them. And these are average of the last 12 values given in the time series data. Last 12 data given, the average is 172.95. So Excel is thinking I have committed an error. So I will say ignore error, ignore error. So my 12 period trend component SMA values are there. Next, I will calculate something called seasonality, seasonal component. What is seasonal component? We will try to subtract. Suppose this is, now I have to tag it. I'll tag the months now. Sorry, I will create space for a month. Month was there, I forgot to copy it. I'll create space for a month data. Month was there, yeah. Yeah. So now this is for tagging purpose. Oh, again, this thinking I have committed an error. Ignore error, yeah. Now this is, so you have to tag it. The January value, uh, 12 period is taken in July. Sorry, I have taken it in June. So ideally 12 period should be taken in July. So I'll just take it down. Done. So this is the average of first 12 values and this is the average of the last 12 values. No mistake. So we have taken the trend component 12-month SMA. Now the seasonal component and we have residual component. This is using the STL decomposition, seasonal trend decomposition using LOESS. So seasonal component I am doing it for the month of January. Now you see January original given data is 181.2. From there I will subtract the moving average is 175.25. So you have to tag it for the month. So I will do very slowly. January month 193 point, so 130 minus 1. Yeah. What we'll do, we will, so we have this one, so we have only 12 values here, only 13 values, only July value repeating. So for January we have only one value. So that value will subtract. So 193 minus the January trend value, which is 175 will do. And also again here we'll have 181 minus 175. So this is for January. Now for February, this is 151 minus this. And this also for the February. So we can now drag till June. Here also we can drag till June. And now July, there are two values 175.94 and also 172.95. I'll take as average of this. So we take 176 minus average of this and this, average of this and this, that is 1.85. Yeah, and here also I'll take 179.4 minus the average of this value and this value. July value appeared twice, that's the reason. So now again I can do for August. Till December, and then again we can do it for August value will be was 63 minus the August value here is 174 moving average. So these are the seasonal component ST. So we have got the seasonal component Now we have to find the residual components wherever we have the values. So we have values July to July, July to June. So we'll find the residual component by this minus this minus this. So July will be a non-zero value, otherwise it will have zero values because we have not taken average. So in July taken average, we have this is the residual component here. So this is called a time series decomposition. So we have learned how to do a time series decomposition using STL method, seasonal trend decomposition using LOESS. We have taken a 12 period SMA and took a seasonal component by subtracting it. Subtracting, the formula is YT minus TT we have taken. So this is YT, this is TT. So this is YT minus TT. So wherever TT, the month suppose is July, July appeared twice. So we took an average of 175 and 172 and subtracted 176 minus the average. But for say August, we had only one single value 174. So for August, we have taken 163 minus the 174, that moving average, that trend. So this is the time series decomposition. So I stop it here today. So we have, I just revise. We have today learned stationarity and non-stationarity. First, I spent a lot of time on to check whether the given time series data is stationary or not. We have broken down the time series data into 4 parts, then use SMA and rolling standard deviation, also visualized it. Then we have done an autocorrelation factor test, and also we have done an augmented Dickey-Fuller test. All three methods we have got the same conclusion: the given data that we have considered is non-stationary. Then we have taken that non-stationary data in the second worksheet and we have tried to achieve stationarity by using differencing technique, and we have seen it is not possible to achieve, and I have given the reason also. Then we have used logarithmic technique transformation and we achieved the stationarity with a very narrow range, and we are given the reason why we could use logarithmic transformation here, because the mean and variance was changing, trend was not visible. Then use a detrending technique and we could not achieve the residual stationarity, and we have given the reason why residuals are non-stationary. And then we have used a time series decomposition just to show that how this works with TT and ST. This is the seasonal component ST. And this is the residual component. So with this, I stop here today. I'll send this Excel file and the PPT uh, in so that you can go through them. And with your permission, I'm stopping it and sharing the Excel sheet and the PPT. Only one Excel sheet is used. Please understand there's a sheet 1 and sheet 2 within one single Excel file. So one file with 2 worksheets. So when you get the file, click in sheet 1 where stationarity is being checked, non-stationarity is being checked, and sheet 2 where we converted non-stationary data into stationary data. So both the worksheet has to be checked. So this is for today's class. We have a one last class that is on next Saturday I will take. We'll talk about the Garch model and also we'll revise ARIMA, the auto regression integrated moving average. So thank you so much.